I'm looking at about 3 hours here, maybe just a little bit more because of the delayed start. Otherwise, I'm going to be making reference to the TR-ATM manual. Did everybody get a copy of that or have access to it? And again, to answer, you're going to have to unmute.
Detroit did not get its documentation.
Okay.
Yeah, Calverton's okay, I believe.
Okay, and Houston?
We have our documentation.
Okay. Well, I'm going to make reference to the course schedule, and this is on page 1-3. So I'm going to go ahead and throw that up there. Can everybody see this? Or locate it?
Calverton sees it.
Everybody else got it? Detroit, Houston?
Yes, we see it.
Okay.
No problem.
Yeah, we got a...
Maybe just have them let you know if they don't get it.
Okay. Yeah, but I guess rather than me asking you if you guys got it, if you don't see it, let me know. Okay, otherwise the first thing I'm going to be going over is what is ATM. This will be like about the first hour's lecture before we take a break. Cover the ATM concept and why we use ATM. I'm going to compare ATM networking technology to other networking technologies. And then lastly, discuss how Cray implements these new technologies. And then we'll take a break. The second hour, we'll take a look at the ATM stack, the ATM cell, and we'll start taking a look at the ATM model. And we'll take a break. And then lastly, we'll take a look at the ATM adaptation layers and how ATM makes a connection and the connections using switches. Okay, also, I guess you can see on the bottom of that same page, I'll throw this back up here for Detroit. This was part of an ATM workshop that was offered, I think, a few months ago. And it also discussed some of the software implementation and installation procedures, which is just day 2 information. And the intent here is not to go over that. I will make mention that SPT does offer 2 other video conference courses on ATM. One deals with the bus-based gateway and its implementation, and the other is a J90 and EL series ATM implementation. And those can be requested through SPT. And I'll probably summarize some of that stuff at the end of the lecture. So if there's no questions, I'd like to go ahead and get started. Okay, this first slide here is page 1 from the What is ATM section of your handouts, or your reference material. And this is what is ATM. Okay, well, ATM is most associated with automatic teller machine, but that's not the case for what we're going to do. So ATM is an acronym for Asynchronous Transfer Mode. Okay, Asynchronous Transfer Mode, or I'm going to refer to it as ATM for the rest of this video conference, is going to be one of the fastest ways of communicating, exceeding the 3 most common communication methods known now, which is telephone, telegraph, and, well, tell another person. Okay, I'd like to first take a look at the current communications that exist. So this is a background here. So I'm going to jump to page 2. And here this slide just shows the current communications. Okay, first of all, we have the plain old telephone service, or referenced as POTS. And that's just saying that this communication is transported through the public switched telephone network, or the PSTN. Okay, a lot of ATM is based on this system. Okay, another type of communication we have is telex, which is the old network of teletypes that's kind of obsolete now. Okay, slide down the slide here a little bit. And then for the computer implementations, again, we also transmit that information through the PSTN or the internet. Okay, another type of communication yet is television. And here we have a couple different mediums of transport for this communication. It can be broadcast via radio waves, cable, or the CATV or satellite feed, community antenna TV. Okay, and then lastly at the bottom here, and if this doesn't show up quite clear, just let me know. We have the computer data being transferred in the private domain, which of course is across a variety of LANs, token ring networks, and other networking topologies. Okay, so we have a lot of different ways of transmitting information. The idea was to incorporate all this onto a single medium, to combine all this to make it look seamless, or to put everything on one wire. So on page 3, the early implementation to solve this problem, to put everything on one wire, was the ISDN, or the Integrated Services Digital Network. Throw this slide back up here. So ISDN is the early solution, and then ISDN is based on service rates, and those rates are shown on the page. Skip down to the bottom here. Okay, ISDN was okay for low to medium transfers, and just for some other history, the standards took a long time to develop, and then lastly, and most important to us, is it's not scalable. Plus, with the newer technologies coming out, ISDN networks are easily saturated and bogged down. So that's where ATM is taking over. So it's going to be an extension of the ISDN solution. Okay, on page 4, this is just trying to emphasize this. Throw this slide back up here. Just focus in on this here a little bit. Okay, so this kind of shows some of the typical bit transfer rates for some of the networking technologies. So voice transfer, or also referenced as constant bit rate, is the lowest. And you can look down this sheet, and it ends up with, at the very bottom here, HDTV, which is coming out, which is going to take up the most bandwidth. And if you look at the previous sheet, you can see that a lot of these transfer types, or these services, exceed the ISDN allocation. And then lastly, at the bottom of this slide here, kind of graph on how much bandwidth or networking that these types of services require. So this kind of throws ATM and some of the other networking technologies in a comparative view. Okay, I also have a few other slides coming up which also kind of go back and rate ATM to the others. Okay, again, if there's any question, just go ahead and speak up. I think if we can keep this really interactive between all these sites, it should make things go by pretty quick. Okay, otherwise, jump back. This is page 5. So the vision for ATM is to put all these things across one medium. Okay, so just to start getting into ATM, this first bullet here says ATM network smooth cells. Okay, they're of a fixed length, where a lot of other cells or packet technologies or rings can have variable, which increases delays and and slows down transmission. So because we're fixed packet here, or fixed cell lengths, there is very low delay between transfers, and all transfers are very high speed. Okay, and transfers go from a source to a destination, and then endpoints, as it shows here in the second bullet, are responsible for reassembling data where the transmitting device segments it off. And then on the very bottom here, we kind of show all these services I talked about, voice, video, and data, being transmitted to some customer premise equipment. Okay, also make note that there is just a bazillion ATM acronyms, so if you lose track of them, just go ahead and ask. I don't think that there was a glossary at the end of this book. So if the acronyms start getting overwhelming, just go ahead and speak. I think most pages define them all. But anyhow, ATM, excuse me, will take all these types of services through some customer premise equipment and transfer these fixed length cells out into our ATM network. And then from there, as that second bullet mentioned, the receiving equipment will take these cells and reassemble them and put them into a format that can be used at the destination end. So the key points here is that we're fixed length, and all services will be transmitted across one single wire. Okay, this next page, page 6, this is just a little more background on ATM. Okay, ATM was selected by a few standards bodies to replace the ISDN. And here we just point out that CCITT and the ITU were responsible for selecting the ATM protocol. Excuse me, trying to get over a flu here. So if my voice fades in and out, I apologize. Okay, ATM was pushed mainly by vendors and users into the marketplace, so ATM is rapidly being accelerated. Okay, not all the standards are defined yet, but I'll talk about that at the appropriate time. And some of these standards should be coming up into resolution here, hopefully by the end of the year. Okay, and then ATM was designated to be used with the synchronous optical network as the physical layer, or they also refer to that as the SONET network, and I'll be talking about that more a little bit later on. And then the standards committee agreed on a fixed cell length. Okay, we're asynchronous, and because we're using a lot of the existing technology based, or I should say we're leveraging a lot of our ATM technology on the telephone system, which is synchronous. So on page 7 here, we talk about the comparisons for asynchronous versus synchronous. So here we're just saying that the synchronous is slower than asynchronous because each node on our network has to sync up with a clock, transfer information, where asynchronous does not. Therefore, asynchronous, as it says here, is the best way that we can transmit data. However, there's provisions in the protocol to transmit ATM cells in a synchronous state, which addresses the constant bit services required by voice. Okay, I should probably mention that there's a lot of details that go into the ATM and STM. There's a book currently in logistics. There's 50 copies of this book. try and zoom in on this. This can be ordered, and this is where I'm also basing a lot of information on. Alright, and this is the Asynchronous Transfer Mode Bandwidth for the Future. And this is a book that Telco Systems puts out. So, if you're interested, that also covers a lot of basic ATM implementation. Okay, so to summarize, throw a few questions out. So do we have a fixed or variable length cell for ATM? Somebody want to jump in and answer that? Just trying to get a little interactivity because it's in the morning and right. ATM transmits information in fixed length cells. Okay, what types of service will ATM handle? And there's 3 basic types.
Voice, data, and video.
Yeah, we got data is one type, video is another, and the third type is, I think I heard somebody say voice. So we got video, voice, and data are the 3 services ATM will handle. And again, these will all be transmitted across one single cable or one single medium. Okay, so next I'd like to go and address why do we want to use ATM? Why is Cray going to do that in particular? Okay, so in the next section, this is in your handout, it's the why ATM section. Well, the main reason why we want to use it, so this is page 1. Okay, the very main reason why we want to go to ATM is because it's scalable. Okay, so, and I mentioned that ATM cells will be transmitted across SONET. This was the target network defined by those standards committees. And this network is very scalable also. Okay, we have several transfer rates, okay, available on SONET, and not all of them have been developed yet. The primary or the slowest rate of SONET transmission is called the OC1, where OC is an acronym for optical carrier. So the lowest rate for SONET is 51.84 megabits per second, and then everything is based on this transfer rate. And I see some people that showed up in Egan, so I'd like to. We got Hugh and Rod, Hugh, Shane, and Rod in Egan. Can you guys hear me okay? You may have to unmute your tablet. Okay, well, I'm hoping Egan can hear me. Yeah, if you can hear me, okay, thanks. Just want to make sure you can hear. Okay, the OC1 standard is fully defined. However, we don't use it here at Cray, and I don't believe anybody else uses it. However, the next level, OC3, has been developed and defined, and currently this is the ATM implementation that Cray uses. And as I might have mentioned before, we currently implement all iOS E systems, or Model E systems, with OC3, and all EL and J90 systems are capable of implementing the OC3 standard. Okay, just to give you a little more history on the Cray implementation, is that we're going to support OC3 until the end of '96, and then around fourth quarter of '96, the OC12 implementation should be developed, and implemented, at which time we'll offer that scalability to our customers. Okay, and the OC12 standard is 622 megabits per second, or it's 4 times the OC1 transfer rate. Okay, the next level is the OC48 standard, which would be 48 times the OC1, or 2.48 gigabits per second transfer rate. And just to let you know, OC3 and OC12 transmission rates max out our current I/O capabilities for Model E and J90EL implementation. And the current implementation for the new I/O, the IOSF or the scalable I/O, which will be the follow-on or replacement for the IOSE, won't be able to support OC48, so Cray's got a committee spawned off here in engineering where they're looking at creating, or the feasibility of engineering our own OC48 implementation, which would hook directly to the Cray GigaRing, or the former SCX channel, if you're familiar with the new I/O technology. And we're looking at a potential OC48 implementation in 1998. And then by the year 2000, and this isn't on your sheet, so you may want to add it, we're going to be looking at an OC, hopefully this shows up, an OC192 implementation, which transfers information at 10 gigabits per second. Does that show up fairly well, the pencil? Okay, if not, just let me know. I think I have a few other notes written on various other slides. Okay, so currently OC1 is not supported. We currently support OC3 on Model E systems, J90 and EL systems, and at the end of next year we should be implementing OC3 and OC12. Okay, on page 2, I'm going to jump back to the slides here. Okay, another reason why we want to use ATM or implement it is because ATM application is transparent. Okay, and as I had mentioned earlier, that we can transmit all these services across a single network, so we don't have to have a cable for sending video, we don't have to have another wire for sending voice or broadcast video through the air or send across a separate cable. All this can be put on one cable. Okay, and then on the bottom here of page 2, another reason why we want to use this is because ATM is very efficient and flexible. And by that I mean the network can be very granular, and that we can specify a quality of service or declare a bandwidth. Okay, and the network can be reconfigured. It can be reconfigured on the fly to match applications. Okay, so this efficiency and flexibility is good for the software end because, and I'm not much up on my software side, but some of the limiting factors of software applications is the network. And that, I guess, can have an impact on why applications are designed the way they are. Okay, with ATM we can expand our network or allocate bandwidth to support large applications. Okay, and I want to go back and focus on the granularity and the quality of service, or the QoS. And this is not in your book, but I just drew this up real quick. Okay, what I want to show here is this will be our bandwidth that we're transmitting on. In this case, I'll just say it's our SONET. And the administrator, and there is some administrative overhead on ATM networks. The system administrator will specify a quality of service, or this will be some parameter in the operating system. And here we've specified it to be at this level. And we can, here I'm just showing that this application is using this much bandwidth, and this will be the unused portion. Well, I can go back and tailor the bandwidth and knock it back down here for this application, opening up other bandwidth for other applications. Or for large applications, I can open up the whole bandwidth and give it everything. So I can scale the bandwidth by setting various parameters. Okay, in addition, I can also set up multiple channels, which I'll be talking about more in depth when I talk about the ATM cell. We can allocate a lot of channels for one particular application. Okay, the next thing I'd like to take a look at on page 3 is the summary of comparative technologies to ATM. So what I'll do is I'll just let you take a look at this. There's a lot of information on here. And if the Detroit location, if you want me to move this around so you can see it a little better, just let me know. Otherwise, across the top, we're pointing out the various current networking technologies that are being implemented by customers. And way on this far side here, I'm going to move this around, is ATM. So we were just listing in this top column, the standards, or the standards bodies that implemented these networking technologies. Talk about the service type. So again, here we're cell, and ATM is basically a switching technology. Okay, some of these other things I'm going to be talking about in a little bit, so I'm just going to briefly skip over them. The PDU, or the protocol data unit, can be variable. Okay, this is the current bandwidth that we implement, and this is in megabits per second. Okay, this is just saying that our ATM cells are 53 bytes, and again we're fixed, so that's how big an ATM cell is compared to some of the others. Okay, the service type is essentially a connection technology, or it's connection oriented, but I'll also come back and talk about some of the service types. And then the ATM also provides for error detection over here, and then way in the bottom of the corner here it says error correction, but the system administrator can toggle the error correction on, so this can also be a yes down here. So that's a quick rundown of the comparative technologies, and some of the other items, ATM specific, I'll be addressing throughout the video conference. Okay, on page 4, send this across. Okay, this slide here, we're just showing some other enterprise service comparisons to ISDN, X25, and frame relay as it deals with the different types of services. So while some of these can be backstitched to support video and voice transfers, ATM handles all of them. And again, that was to make for a seamless, transparent network. Okay, at this point, are there any questions on what is ATM and why do we want to look at, or why do we want to implement ATM? All right, otherwise, I want to take a look at the ATM stack, and then I think we'll go ahead and take a break. So this is just a few more slides. Okay, so this will be from the ATM stack section, page 1 of your book. Okay, so this is the ATM stack, and this is comparing the the ATM protocol to the OSI model. And I'll give you a couple seconds to look this over. Otherwise, on the ATM side, at the bottom here, we define the physical layer. And I'm going to talk about all these layers in a little more detail. So this, you may want to pull this page out and make reference to this as I talk about each of these individual layers in a little more detail. And then the next layer going up toward the application you can see is the ATM, which will interface the ATM adaptation layers to the physical layer. And then we'll be defining our data transfer and the types of services and networks that we'll be operating under. Okay, I should mention that currently Cray does not support signaling, so this really isn't being used. And then lastly, the actual application. So anytime we're transmitting something, our application goes down through the stack, and whenever we're receiving information, we go up the stack. Okay, so the first portion of the ATM stack I'd like to take a look at, this is on page 2, is the physical layer or the medium dependent sublayer. So I'll jump over to this. Okay, what this layer is going to give us, and this is defined by the those standards bodies, is it provides the bit timing, line coding, loopbacks, and defines connectors. Okay, so bit timing and line coding are used to support connectionless type transfers, and I'll be talking about this here in just a second. Loopbacks provide for a software loopback for either maintenance or diagnostic troubleshooting, and then the connectors define how we physically hook up to the network, and I'll talk about those in a second here. And because of these, we can use existing technology. Okay, and those technologies that are approved by the ATM forum are listed here, and then I'll talk about the ones that Cray implements. Okay, so of the approved ATM technologies here for the physical layer and medium dependent sublayers, we're divided out into multi-mode, single mode, shielded twisted copper, or shielded twisted pair, and then the very last one down here is coax. Okay, I'd like to just talk about the multi-mode fiber. Okay, all multi-mode fiber is LED-based optical transmission. So we're using a light emitting diode to transmit our optical signals. Okay, we have 3 types of multi-mode fiber implementations, and they all use the 62.5 micron fiber network cable. And of the 3, we have a 100 megabits per second implementation, which is the line coding for a 4 to 5B encode decode. And this is when you are going to be encapsulating ATM cells onto FDDI networks. Okay, Cray does support this. And the Cray implementation is also referred to as TAXI, which is an acronym for transceiver. Wait, I've got this written down here, I always forget it. The TAXI implementation is an acronym for Transceiver Asynchronous Transceiver Interface. Okay, and Cray does support this, and again, if you recall, the OC3 implementation was 155 megabits per second. Well, because FDDI token ring networks operate at 100 megabits per second, the physical layer is going to reduce our speed here, but we can encapsulate ATM cells onto FDDI networks. Okay, the next type of multi-mode fiber is the 155 megabits per second SONET implementation. Okay, SONET is also referenced to as STS. And I'll be talking about SONET networks in the next slide, as a matter of fact. So I'll just say that the OC3 and STS3 imply the same thing, or 155 megabits per second. Okay, Cray does implement the 155 megabit multi-mode fiber implementation. So this is supported by Cray. Okay, the last type of multi-mode is the 8B, 10B multi-mode fiber. Okay, if you're familiar with the IBM standard for SCON, which is an acronym for Enterprise System Connection. Okay, that protocol defines transfers on those types of networks. And the network, an SCON network can support 200 megabits per second transfer rate, but ATM maxes out at 155. Okay, it's also referenced to as an 8B, 10B encode decode. But I'll mention that the 8B, 10B implementation is not supported by Cray. So this is the only one that Cray does not support. We do sell SCON interfaces, but we do not encapsulate ATM cells on them. So that's not supported. All right, the next type was the single mode fiber. Okay, and here we're pretty much the same as multi-mode fiber, STS3 implementation, except that single mode uses a laser to transmit its information rather than an LED, so that's the primary difference. Okay, Cray does implement the single mode fiber. So we support the two multi-mode fiber, Taxi and SONET, and the single mode SONET, with the primary difference being LED and laser. Okay, and for the connector types, Cray supports the SC and ST connection on the connectors. Okay, the next implementation is shielded twisted pair. All right, this is the same implementation as the multi-mode fiber 8B, 10B implementation, except with the multi-mode fiber, we're transmitting our information across an optical network, where this is a copper network, so it's using a different medium to transmit data, but it's the same protocol. Okay, and the last is coax, which is basically 10 base T. So we're encoding our ATM cells across like an Ethernet network, or we're transmitting information on a T3 or a DS3 copper-based medium, and that has a transfer rate of 45 megabits per second. Okay, and then lastly, in the bottom here, it says that these standards are under development here. 52 megabit and 155 megabit unshielded twisted pair, CAT 3 and 5. Okay, the last four these last ones that I talked about, the shielded copper pair, the coax, and the CAT implementations are not supported by Cray Research. And again, that was this physical layer that I just mentioned here in this ATM protocol stack. Okay, the next layer going up is the ATM. But before I talk about ATM, I'd like to elaborate just a little bit more on the Synchronous Optical Network, or SONET. And this is what, again, the network that the ATM standards panels are targeting So this is page 3. Okay, and this is the medium most associated with ATM, but again, we can encode cells to be transmitted on FDDI networks. Excuse me. Okay, and then STS is an acronym for Synchronous Transport Signal, as referenced by STS and then N being the implementation. Okay, and this is just again a review of the OC3 implementation. So again, we have OC3 currently being implemented. So then when we encode this on our SONET, it becomes STS3, which implies 155 megabits per second transfer rate, where STS12 would imply OC12 implementation, and et cetera. And again, the long-term implementation around the year 2000 will be the OC192, or when this is put on SONET, would be the STS192. Okay, then STS indicates that this is a transmission framing specification rather than the optical signal. And then again, lastly, in the bottom of the page, make reference to the OC standard, which defines the optical carrier. Okay, so next we'll take a look at the ATM layer, and this is off of page 5. Okay, so this is what the ATM layer is going to do for us. Okay, it's going to take care of cells, and I'll be talking about cells after the break. But it's going to insert and extract cell headers. It's going to handle our addressing. It's going to handle our cell flow control into and out of our node. It's going to handle cell multiplexing. And again, it's going to perform a higher level of loopback. And I will be kind of getting into each of these areas a little more in depth when I talk about the ATM cells. Okay, so if you refer back to page 1, the next layer to go up to is the ATM adaptation layer. Okay, there's several types of ATM adaptation layers, and I'll refer to them hereafter as AALs. Okay, on page 6 here, we kind of give the big picture of AAL service. Okay, and the main point here is that this service is going to be taking our application data, and it's going to start formatting information into our fixed cell lengths. So we're going to be taking information and cutting it down, or I should say, if we're going to be transmitting this information, we're going to be segmenting it down into fixed length cells, or if we're receiving information, we're going to be reassembling it from our fixed length cells back into our usable data. Okay, depending upon the type of service, whether it's voice, video, or data, we'll be using different AAL services, and I'll be talking about those more after the break. Jumping back to the slide, this is a quick rundown of what the AAL portion of our stack is going to handle. Again, segmentation and reassembly, or hereafter referred to as SAR. Okay, it's going to handle the sequencing. If we get fragmented cells, it'll put them back. It'll reassemble them in the correct order. Okay, it's going to be doing a CRC check. We're checking for data validity. Okay, and depending upon our service, it's going to give us an indication of length, and I'll be talking about this more in depth with each of the different AAL implementations. And then lastly, it's going to allocate a buffer size. So that's a quick rundown of what that portion of the stack is going to handle for us. Okay, the next layer is the data transfer layer. And, excuse me. And I'm just going to go ahead and jump over to page 7. Okay, what this is going to do is it's going to be working in conjunction with the AAL layer and the top of the application stack. Okay, I mentioned that there's a variety of services. In this chart here, it's going to be showing the different services that AALs will handle. So we have 4 different classes that we divide our services off into. First being Class A, which is going to handle your bit rate is a constant bit rate. Okay, your connection type is connection oriented. Okay, there's no delay in the timing of your transfers. And then lastly here it says this is most used in voice and conventional video. And conventional implies that it's uncompressed. Okay, I'll just give you a second to kind of look over the rest of the classes. Class B, C, and D. So essentially we've got 4 classes, and different AALs are going to be associated with particular classes. Okay, jumping ahead, page 8 is going to show the layered architecture. So this is just showing that the physical layer and the ATM layers of that protocol stack are the ones that are talk directly across the ATM network between a source and a destination node, and then the upper levels, the AAL layers, communicate virtually through the stack. And then the key bullet again down here is that we have different AALs for our different services. Okay, and then lastly it says when we transmit information through the network, data is not being analyzed. Okay, the last page in this section, and then we'll take a break, is kind of the summary page for this whole ATM video conference. And it's kind of busy. There's a lot of information on it. But this is comparing all the layers of AAL, and I should mention that we have 5 AAL layers. And these are kind of pointed out here. 1, 2, show 5, and then there's a 3 and 4 layer. Okay, I should mention that currently Cray only implements AAL5. Okay, AAL 1 and 2 are not fully defined by the standards committee yet. Okay, we do kind of implement portions of the AAL3 and AAL4 adaptation layers, but we currently implement AAL5, which overshadows 3 and 4. I should mention that. Okay, so you can kind of see that on this slide here. Just a couple last minute things to mention, focusing on this a little bit more. If you look at AAL5, that's mostly associated with Class C type service. Okay, but we also do cover Class D, which will be data in both an uncompressed and compressed format. So I think that's kind of all I want to talk about the ATM stack. Are there any questions thus far from any of the locations? All right, if not, why don't we go ahead and take a 10-minute break, come back, and I'll take a look at the ATM cell. Start off with that. All right, so I'll see you in 10. Okay, just a few questions on some of the stuff we just covered. So I'd like to address Cray's implementation. So the first question is, what types of systems does Cray implement ATM on? 3 system types. Okay, I heard all the correct answers. Could you say them a little bit louder, just in case the other sites didn't get a chance to hear that?
You have multi-fiber SONET and single mode fiber SONET, and you have the taxi.
Okay, yep, Cray supports multi-mode fiber and SONET, and the other one was taxi, or the FDDI implementation, and single mode fiber. Okay, Cray has 3 types of systems that these implementations can be put on, and those were systems with a Model E, with an iOS E. So all Model E systems can run these types of ATM implementations. And it does that by using a bus-based gateway. And I have a picture of that here. See if I can send it to you. All right, what I have showing here is this is a C90 with an iOS Model E. And for Model E systems to become implemented with ATM, we encapsulate our ATM cells onto a HiPi network. Okay, I don't think you have this exact picture in your notes or in the material provided, but they do show something like this on page 5 of the What is ATM section. So if I can. So it was off of this page right here. So it's page 5 of the What is ATM in the front of the book. So what they're showing here is a T90, a Triton with a BBG. But for any system incorporating an iOS E, we encapsulate all ATM traffic across the HiPi network, and then we have this external network device called a bus-based gateway, or a BBG for short. And then what that does is it converts, or I should say what it does is it takes our encapsulated ATM cells from HiPi and removes all the HiPi framing structures and transmits the cells out onto our network. And if I could just drag this down, this is kind of a block diagram of this thing. But over here, this is our iOS E. Okay, this also is not in any of your in any of your handouts. What we have here is our iOS E and our HiPi board set, which is the HCA3 and HCA4 source and destination. That's what these stand for here. Interface an S-Bus HiPi card, and we buy this from an outside vendor. And then we have a Spark processor which handles all our framing for HiPi, for either encapsulating ATM cells or removing the HiPi framing structure, and puts that up onto our S-Bus ATM card. We also buy this from an outside vendor. Okay, our current vendor is Forest Systems, but we're going to be moving to another vendor, I believe is Interface. Otherwise, after that, then we have our actual ATM traffic, which is sent out to the network. Okay, we have essentially 2 types of network mediums that we can send our ATM traffic across based on our multi-mode implementation. And what were those 2 types of network mediums, or network protocols? Okay, the first type was Sonnet, and that had a transfer rate of 155 megabits per second. And the second implementation was of the multi-mode fiber was Taxi, which was the ATM encapsulation on FDDI networks. Okay, also the J90 supports all these implementations. And if we take a look back on that page 5, okay, we can hook up our ATM cards directly to the VME I/O of the EL or J90 systems, and we do not need this external conversion like Model E systems do. So EL and J90s directly connect to the ATM network. Okay, I will mention that after the new IO, the new SIO or the IOSF, however you may have heard it referenced, when that product is announced, support for the bus-based gateway will be dropped. So around the end of next year, end of '96, the BBG will be dropped, Cray will no longer support it, and Taxi will no longer be supported. So it'll be strictly Sonnet. Okay, any questions on the Cray side of what we're doing with ATM? Okay, what AAL is supported by Cray Research?
5.
Correct, yeah, AAL5 is the supported adaptation layer. Okay, I think that's the main thing what I wanted to hit on. Outside the fact that the difference between multi-mode and single mode was that single mode is laser based and multi-mode is LED based. Alright, otherwise I'd like to jump ahead to the cell section of your handout or the book. And on page 1, the basic unit of anything is a cell. Or I should say the basic unit for ATM is a cell. Okay, the cell is basically broken up into 2 parts. We have a payload section, or this white part here is a payload section, which is of a fixed length of 48 bytes. And then we have a header section, which is a fixed length and is 5 bytes. Okay, all transfers are done in fixed length cells, so the whole cell here is 53 bytes. Okay, there's some background information on the cell structure here, just kind of like to go through. So this pretty much sums up what I think I just mentioned. Okay, the header here is used for routing and defines some of the transmission services, and then the payload contains adaptation layer data and or application data or user data. So then this table down here also kind of talks about what's included in each cell. So you have these types of information also being encapsulated. And we talk about the different services for AAL. We'll come back and touch on these. Otherwise, each of these things comprise one cell. All right, for some background information, this is jumping over to page 3. Okay, well, we already know that the cells for ATM are a fixed length, but here we're just trying to show why they went with fixed length over variable. So here you have different cells of various length and cells of a fixed length, and the advantages and disadvantages of variable sized cells. And I think the primary disadvantage why we went away from variable length cells is that there's delays and there's higher overhead, which is the main reason. Okay, a little bit more background information about the cell is that the Standards Committee, the ITU and the CCI-TT, didn't quite come to an agreement, so it's kind of like the government shutdown situation, couldn't come to a consensus. So one standards panel wanted 4-byte header, the other wanted a 5. And I believe that this is shown on page 5, the North American versus European, what each wanted. And then how the header should be defined in terms of addressing, payload identification, specifying qualities of service, and then network and congestion corrections. So these are on the bottom of this page 4 here, shows the 2 proposed cell structures. And this next slide here on page 5 just shows that between the 2 standards committees, they came to an agreement based upon what the US, or the North American standards committees and European wanted. So between the compromise, we came out with the 48-byte payload and 5-byte header. So that's just some background information on why the cell is defined the way it is. All right, on page 6, this next slide here talks a little bit more of the bigger picture of ATM networks. So the standards also came up with interface definition protocols, and they're essentially broken up into 2 main areas. Okay, the first is UNI, which is an acronym for the User Network Interface, and this defines how private ATM networks transmit their information. Okay, the second type is referenced to as NNI, and these acronyms are on the bottom of the page also, which is the network interface. So this defines how ATM traffic is transmitted across public ATM networks. Okay, the main difference for public and private switches that we list here between UNI and NNI is defined by the physical layer and the carrier type. So that's kind of what defines public versus private UNIs and NNIs, is the physical layer that the switch is set up as and the connection between them. Okay, the UNI switch or UNI networks are usually equipped with the ATM switch and some sort of adapter to a private UNI ATM network, where NNI doesn't have that adapter. It's simply just a switch to switch. So that's another differentiation. For Cray's main focus, Cray is only concerned with UNI networks, or the protocol for UNI. So Cray is only interested in the private UNI connection. Okay, keep in mind though that these connections right here are targeted to be SONET. So this will be your 155 megabit fiber optic medium. And then through the end of '96, the other type of UNI that Cray supports is the FDDI, or that taxi. So those are the only 2 things that Cray is looking at. So I should also mention that private UNIs become public when they're hooked up to NNIs, which, jump back here, which is this connection here. So that's kind of the hierarchy of UNI versus NNI. Okay, otherwise, to focus a little bit more on the ATM cell structure, and the basic format here is on page 7. Shows the basic structure. Is that, again, this is just showing we got 5 bytes of header, 48 bytes of information or data payload, and then the note on the bottom here says that if you're reading through some ATM information, that the bytes are also referred to as octets. Okay, otherwise on page 8, this is just saying how the ATM cells are broken down and transferred. So to follow along with the bulleted list on the bottom, just says that bits are sent within the byte are sent in a decreasing order, or the most significant bit 8 is always transferred first. Bit 1, the least significant bit, is sent last. And then the first or lowest numbered octet is sent first. So then, if we're going to send this frame across the network, bit 8 of the first byte is sent first, and then bit 1 of the 53rd octet is sent last. So that's all this slide's trying to show. All right, the next slide shows the structure of the ATM cell, and then we'll talk about each particular facet of the header, and then lastly the payload. So on page 9, these are the functional units of the cell. Okay, in the first octet here, the lower bits specify a virtual path, and that's used in conjunction with the virtual channel. So this provides our addressing to specify a destination. Okay, the upper 4 bits of the first octet specify a generic flow control. Again, I'll be coming back to each of these and talking about them briefly. Okay, down here on the 4th octet, we have a cell loss priority bit, and I'll talk about that. It's usually used in conjunction with this field up here, the generic flow control field. Okay, we have a field that specifies what type of payload we're carrying. And then the last byte of our header is a checksum on the header. And then lastly we have our payload. So what that's showing us is the basic format. So the first field I'd like to go ahead and take a look at is the generic flow control field, which again on page 10 here will be the upper 4 bits of this first octet. Okay, I will mention that the generic flow control field has not been fully defined by ATM standards, so this can vary between ATM implementations.
When you were discussing the header a few minutes ago, was that an AAL5 header? Because I know the headers changed slightly according to the adaptation layer.
Okay, this header, let me jump back. Are you talking, what particular page?
9. When you were talking about the full header.
Okay, this full header here, okay, this does not define what particular AAL we are. Okay, the AAL will be defined, or that information will be carried in the data payload section.
Well, the address fields changed with the AAL though in the header. The interpretation of the address area. There are some fields that are defined in some of the AALs that aren't used in the others.
Okay, yeah, that's, well, okay, this is jumping ahead just a little bit, but yeah, certain AAL services will require further addressing. But that's separate from the cell header. So there will be like a subheader which will be carried in the data payload section. And I believe the next section after the cell, they talk about the they talk about the various AALs.
Okay.
Otherwise, the cell header that's on page 9 is used to identify a path and a channel to a destination. So that's all this information contained here, and it does not reference any AAL type of information. So, hopefully when we talk about when I talk about the different AALs, we'll come back and talk about some of the addressing and the tags, or the headers and trailers assigned to the various AAL adaptation layers. Okay, otherwise I'm going to go back to page 10 and talk about the generic flow field, control field. Okay, and again, this was not fully defined by ATM standards. Okay, this is a 4-bit field, and it's only used to control traffic across the UNI. So Cray's implementation of the GFC field may be different than another company's implementation. And again, the UNI is the private ATM network. Okay, I think I just lost a site. Can everybody check in real quick? Name off your location.
Calverton's here.
Okay, I see Calverton.
Houston's here.
Okay, Houston.
Yeah, we're here.
Okay, do we got
Detroit's here.
Detroit?
Detroit here.
Oh, I must have got, okay, I think I'm looking out your window. That's what that is. Egan?
Can you hear us?
Okay. Okay, somebody must move the camera. Okay, let's jump back to the GFC field. All right. So we're only using it in the UNI implementation, the GFC. Okay, and then there's a note here that says the NNI is currently being defined by the ATM forum. And it says it's supposed to be complete in September '95. Okay, I tried to check up on this, and they have not come to an agreement yet. So hopefully by the end of the year, it'll be defined how traffic is transmitted across NNI networks using the GFC. Otherwise, on the bottom here, this field also provides these following benefits for us. Okay, it defines the available bit rate of data transmission. Okay, it also defines our network congestion, whether the network's really bogged down or not. And I'll talk about these two things here in a little bit. But we have the FECN, which is a forward explicit congestion notification, and then the BECN is just the backward explicit congestion notification. And then lastly here we have a virtual circuit flow control, which is the VFCS. Okay, and all these do is it's a way that ATM networks can, I guess, modify the network traffic, cut out any non-essential traffic to keep the more priority types of information flowing at maximum transfer rate. And it's also used in conjunction with that quality of service that I talked about. So that's also where some of this information is being addressed. You know, we can allocate bandwidth and granularity. Okay, I would like to talk just a little bit about the FECN. Okay, so this is on page 12. Okay, what we're trying to show here is that if we're transmitting information across our ATM network, so if this ATM and CPE was an acronym for customer premise equipment, so if this ATM node here is sending cells out, we're going to this switch, And then once we start sending our cells across this network, and this could be either UNI or NNI, if we get a lot of congestion between this switch, what's going to happen here is this switch is going to say, hey, I've been monitoring traffic and it's exceeded the established parameter limit. Okay, and these parameter limits will be specified by the system administrator. But once these parameters have been exceeded, then this cell, this FECN cell, which is just a modification of that GFC field, will go until the destination says, hey, we're having a lot of congestion. You may want to take a look and see if we can take any type of traffic off of this network to speed it up a little bit. Okay, and just to give you a little information, we're also going to be analyzing that CLP bit, that cell loss priority bit. Okay, if we get one of these, if the destination gets this FCN cell, it's going to go back and inform the source that, hey, there's a lot of traffic, and then the sender will adjust flow as established by the parameters set up by a system administrator. So it may halt the transfer, or it may up the priority, or just delay the transfer. Okay, the next type of congestion notification, and this is on page 13, is the backward flow control. And here we're bypassing the fact that a cell has to be transmitted all the way across. If the destination is receiving information and he's too clogged, this will be even before a source node can transmit. If he's being bogged down with transfers, he's just going to send out a BECN cell saying, hey, I'm taking on heavy work or heavy loads of data here. Can anybody delay or drop their traffic coming to me? So this is sent off automatically, and again, these types of cells will be sent based on the system administrator's setup and how they have their ATM network configured. And it's kind of what I summed up here by this bulleted list. So this is where we establish a lot of flexibility in the network. Okay, the last way of handling congestion or allowing for flexibility of network is the VCFC, excuse me, and this is on page 14. Okay, what this is the virtual circuit flow control, and this is the link feedback. Okay, this feature can be enabled or disabled by the system administrator, but what it does is it uses a credit mechanism to allocate bandwidth. So in other words, a station that gets the most credits, or that saves credits, can use them to establish bandwidth. So the more credits a transmitting node has, the more credits that a node that has information to transmit has, can trade those in to get greater bandwidth. So this also allows for that quality of service to be extended, perhaps above what the system administrator's level of quality of service is. So we're just saying here that if this particular ATM node is sending information, but he doesn't have a lot to send, the switch will come back and say, well, since this particular node hasn't sent a lot of traffic, this switch will start sending him credits, and then he can again turn those credits into gain extra bandwidth, or a portion of the bandwidth required to do a particular transfer. And then they're just saying here that these switches, if their traffic is real high or real low, can forward credits off. And again, this will be based on a network load factor, and this will have to be a parameter established by the system administrator. And again, this feature can be enabled or disabled. Okay, and the last bullet on the list there just says it's efficient to do this because we can kind of monitor or expand or contract the network on the fly, but because of keeping track of credits, it creates a high overhead. Okay, so that kind of sums up the GFC field. Continuing on, talk about the next field of the cell header. Okay, this will be page 15. Okay, and here we're going to talk about the virtual path identifier and virtual channel identifier. Okay, and these are usually referred to as the VPI and the VCI. And that'll be the lowest bits of the first octet, the next two octets, and then the upper bits of the fourth octet. And you can see how those are segmented out. Okay, and then the note on the bottom says that these combined fields, which is 24 bits, way in the bottom here, will provide up to 17 million unique addresses. Okay, I should mention that the standards have some of these channels and paths reserved specifically for the standards committee, and that Cray Research only takes advantage of virtual path 0, and then virtual channels 32 through, I believe, 1031. Okay, those are also established by the system administrator. Okay, to kind of tie the virtual path and the virtual channel together, or this field, on page 16, trying to show this physical link. So this would be your fiber cable, or if you're in taxi, then this would be an FDDI, but either way it could, I guess either way it'd be fiber. Okay, what we do is we take a bunch of virtual channels, and these are assigned by the system, by the system administrator. We combined a pack of virtual channels and we group those into a virtual path. And then we can have, based on the grouping of virtual channels, multiple virtual paths. Okay, and then, as I mentioned, that the system administrator is responsible for setting up these channels and paths. Okay, the functions of the virtual channel and virtual path is to route the cell to the correct destination. Okay, I should mention that there are two types of ways that we can transmit information. And what I want to do is I want to go ahead and jump to page, or slide 19. So just to jump ahead a little bit, these are the types of virtual circuits, of which there's two types. Okay, the first type is the permanent virtual circuit, or the PVC, and the second type is a switched virtual circuit, or an SVC. Okay, the PVCs are set up by system administrators, and it's usually used in early implementation. Okay, currently, Cray Research only supports PVCs, or permanent virtual circuits. Okay, the second type was the switched virtual circuits, and this is referred to as signaling. Okay, there is an ATM standard, the Q.2931, and then there's an ITU standard here. Okay, but again, Cray does not implement switched virtual circuits, or SVCs. However, that I should mention, we do have some sites that implement signaling as a software package they buy from Force Systems, our ATM vendor, and that SVC software package is called SPANS. Okay, I don't know what SPANS stands for, probably signaling, some sort of signaling package. Okay, so that's, I guess that's what I want to mention there, is we only support PVCs, and if the site opts for SVCs, then they have to go through our vendor. But Cray does not support that. Okay, on page 20, we show a PVC. Okay, and a PVC, the permanent virtual channel, what we're trying to show here is that this channel is permanent. Okay, it's always there, whether we're transmitting data or not. We're always going to be connected from a source to a destination, as specified by the system administrator through these virtual path and virtual channels. Okay, the difference between PVC and SVC is on page 21 here. Virtual circuits, switched virtual circuits, are made at the connection. So when we're transmitting information, we'll make a connection, and then once the connection is made, then we'll transmit our information. And then when the transfer is complete, then we open up that virtual path and virtual circuit for another transmitting node. Okay, jumping back a few pages, talk about virtual path functions. Okay, so this is moving back to page 17. So here I'm trying to show an example of a PVC, or a permanent virtual channel. So in this case, this example here, we're trying to say that we have some ATM node out here transmitting information who's hooked up to virtual path 5, and then virtual path 5 has two virtual channels labeled 1 and 2 here. When he sends information, he'll be physically hooked up to virtual path 2, and in this case, virtual path 2 has virtual channel 1 and 2. Okay, so it would be impossible for virtual path 5, whatever's hooked up to that virtual path, would be impossible for him to talk to the machine that's sitting on virtual path 1. Okay, so unless a system administrator went back in and set up that connection, those two machines could not talk to one another. Where's that sheet at? Okay, it was mentioned that these fields can be changed. So I'm jumping back to page 9 here. Someone mentioned that the virtual channel and virtual path can be rewritten. And this is true. Anytime we're sending an ATM cell through an ATM switch or across a UNI or NNI connection, as necessary, the virtual path and virtual channel will be rewritten in the header so that it can be steered to the correct destination. The correct destination node. And then jumping again a little bit more ahead, anytime this ATM cell is received by a UNI or NNI switch, we always recalculate the CRC value to ensure that this header is not corrupt. So again, these fields will always be rewritten when they're going through switches. And a new CRC value will be recalculated. Okay, on page 18, here we're just trying to show VCI relationships. So we're just saying that up here we have three different types of service data to send. Okay, we could send all these types of services across one virtual channel and one virtual path, or if we configure this transfer, we can send each service on its own designated virtual channel. Again, This allows for maximum network flexibility that I kind of mentioned earlier. And virtual channels and paths. I don't know if you can see this very well. Try and zoom in on it here. This is something I wrote down. Virtual channels and paths are always specified by the virtual path, and then there's a period or a dot, and then the virtual channel. So if you're looking at something that makes a reference like this, this is the virtual path and channel. And I think in the bulleted list down here, they kind of talk about some of this, except they exclude the VP and the VC. So that's just showing some nomenclature for virtual channel and virtual path. So again, the main thing here is we can send all types of data services on one VCI and VCP, or we can spread them out across several VCIs. Are there any questions on the virtual path or the virtual channel? Again, anytime you pass through a switch, those fields can be changed. Okay, the next field I'd like to talk about in the header, and this is page 23. And also, if I seem to be going too fast here, just let me know and I'll slow down. Okay, the CLP is the cell loss priority cell, and it's just 1 bit, and it's defined on the bottom of the page here. Just says if this bit is set to a 1, the cell has very low priority, and based on the FECN or the BECN or the VCFCN, that was all that congestion control protocol, we can go ahead and drop these packets or delay them. Okay, if the CLP is set to a 1, then it's saying that no, or excuse me, if it's set to a 0, the cell has a very high priority. Do not delay it and do not throw it in the bit bucket. And that's all that field is used for. And again, the system administrator is responsible for setting this or configuring the network either to maintain a high priority or a low priority. Okay, and again, this is used in conjunction with the GFC, that generic flow control field. Okay, if there's okay, I think I'm missing a slide here. Nope, stand by for a second while I locate my other slide. Okay, the next slide is page 22. Okay, what this is showing next to the CLP, we have our payload type indicator field. It's also called the PTI field. And this is going to define what's in our data payload here. Okay, and you can see this list down here kind of calls out the different types of payloads. So this is going to contain information about, again, the payload, what type of information is located in there. And it also is used by the congestion control logic to write those fields to indicate to either a transmitter or receiver that network is congested. Okay, the last type of field was the HEC field, and this is on page 24. Okay, this is the header error control, and all this is a CRC, and this is the last byte in the header, and it's just used to ensure header validity. And as you can see, it uses a BHC code for calculating this. And it says we have 8 bits protecting 32, this bottom bullet here. And it says that it results in an 89% detection, and if enabled, correction capability for single bit errors and potentially double bit errors, or 1 and 2 bit errors. Okay, if you get any error or any miscompare in the HEC, the cell is considered corrupt and is discarded from the network. So that kind of sums up the cell. Well, wait, excuse me, I got another slide here, I guess, to kind of go over. Okay, page 25 calls out some of the HEC control here, so kind of sums up some of the things I talked about. Protects the header, discards the cell if there is a miscompare. You can enable, the system administrator can enable a correct single bit, detect multiple bit type. And again, it's recalculated every time it's received by a switch or some destination ATM connection. And it's got cell delineation for SONET, and they talk a little bit about that more on page 26. So here we're looking for cell boundaries, and just by looking at this, it just says that they're going to check every 5 bytes. Jump back here. We're going to check every 5 bytes until we get a HEC compare, and then when we do, we found a cell boundary, and then we won't then we'll skip the next 48. So then the next 5 bytes we receive would be the header, and then we would know when to calculate our CRC or our HEC. And then it just says that it takes 3 matches to get synced up with the transmission flow. So again, we're checking this on every link because the VPI and VCI fields can be modified. And on UNI implementations, the GFC can also be modified. Okay, so that kind of covers the ATM cell. And again, the cell is used to contain the 3 different types of services: video, voice, and data. Let's see here. Otherwise, the next thing to take a look at was the ATM model and the various ATM adaptation layers. So I'm just gonna start into these here for the first few pages, and then we'll go ahead and take another break. So I think my voice is starting to fade out here. Hopefully I can make it through this last hour. Okay, so the next slide I'd like to take a look at is the ATM model. And this is on page 1 of the AAL section. So here we're going to start combining some of the stuff we've already looked at, such as the ATM cell, the physical network, and the ATM stack. So jumping back here we're combining again the ATM stack as to the physical layer and the adaptation layer. And then we're further defining these layers out. So the ATM layer, or the AAL layer I should say, excuse me, is composed of a SSCS, which is the service specified convergent sublayer. Okay, we're going to be specifying information such as PVC and SVC connection, or the permanent or switched virtual circuits. The next part is the CPCS, or the common part convergent sublayer. Okay, and the primary function here is we're going to start segmenting data to be sent or if we're receiving information to reassemble it, and that's called the SAR, or segmentation and reassembly sublayer. All right, and then lastly we have the ATM layer, ATM salt switching, and then the actual physical transmission media. So here we're going to try and combine everything that we've taken a look at and relaying it to the different types of service. And again, I mentioned we have 4 types of service, and on page 2 we define those out a little more clearly. So these are the services in relation to the ATM adaptation layer, or the AALs. Okay, we have 5 AAL layers, as I mentioned. Okay, and they are AAL1, which is associated with Class A services, AAL2, which is associated with Class B, AAL3, which is associated with Class C, and 4 with Class D. Okay, and then AAL5 covers all AAL3 and 4 implementation, plus it adds features that aren't found by those 2. Okay, which adaptation layer does Cray support? Anybody want to jump in? Okay.
5.
Okay, I got a 5, I got a verbal 5, and a high 5. Okay, and then as you can see by this slide here that AAL5 supports Class C and D, which is also connectionless. If you look at the bottom of the slide here, connectionless and connection-oriented. Okay, again, ATM is connection-oriented on Sonnet, and on FDDI, or the taxi implementation, we're connection-less. So that's what I wanted to point out there. Okay, on page 3, and this is making a reference back to page 1, if you're going up and down that ATM model. This is basically what's going on here in a nutshell. Okay, the adaptation layer structure says we're going to take some user data, okay, and the AAL, when we're going through these convergence sublayers, usually refers to this portion as the datagram. And depending upon the AAL, this can be of variable size. Okay, what we're going to ultimately want to do is transmit information into fixed length cells, which again were 53 bytes in length. So again, based on the type of service, whether we're video, voice, or data, we're going to want to take that information and break it down into these fixed length cells. So to do that, again, we're going to be going through those common part convergence sublayer, which is a CPCSS, or excuse me, the CPCS. So we're going to be taking this information and we're going to take it and identify it from other CS, excuse me here, I'm getting all tongue twisted. We're going to want to take this user information and we're going to put that into we're going to call that a PDU, but when it passes through the first common part convergence sublayer, we're going to want to identify this SDU or this PDU from another one. So a way to identify this is to attach a header and a trailer to it. Okay, depending upon the type of AAL, we're either going to have a header, a trailer, both, or neither. Okay, and then these headers will contain further addressing information and such as required by that particular AAL service. Okay, once we've identified the CPCS PDU from other PDUs of this datagram, we're going to take all this information and we're going to stick it in, or we're going to start segmenting it, because we're going to eventually want to have those fixed length cells. So we're going to take this PDU and we're going to segment it down into SAR PDUs, or segmentation and reassembly PDUs. And then once we've segmented these off, and again, they'll have an associated header and trailer, and it'll contain information such as sequencing so that these cells will be sent in the correct order, and more importantly, reassembled in the correct order. But once we've segmented this information down from here, then we're going to take this information, and this will become the data payload of our ATM cell, and then the lower level of the ATM stack will assign the ATM header, which was that 5-byte header. And then we'll send our information across our network. So that's the overall flow for all the AALs that we're going to talk about after we come back from break. So if there's no other questions before we talk about the 5 AAL levels or layers, why don't we go ahead and take a 10-minute break, and then we'll come back and finish things off.